It gives me great pleasure to introduce Dr. Curtis Seaman to you, and I want to thank Ms. Shawn for making the connection. Dr. Seaman has been with CIRA, the Cooperative Institute for Research in Atmosphere, for about 9 years now. He got his graduate degrees at Colorado State University, which is where CIRA is, up in Fort Collins. And his graduate degrees in atmospheric sciences, and his undergraduate degree at University of Michigan in atmospheric sciences. So he works with multispectral imagery for detecting environmental hazards, including smoke and fires. It's very close to us here. He's won a CoLab award for high impact research, and is going to talk to us about using VIIRS imagery for cryospheric applications like discriminating wet and dry snow and even rain on snow. So very much interested in learning more about that. So please go ahead, Curtis.
All right, thank you, and good morning, everyone. So I'd first like to acknowledge all the contributions of my co-authors and colleagues here at CIRA and at NOAA and the University of Alaska Fairbanks. So I always think it's good to take a moment to look back to see where we've come from in order to understand where we are today. And of course, satellite meteorology got its beginnings with the launch of TIROS-1 back in 1960, where they mounted basically a black and white TV camera onto a satellite. And that satellite wasn't even spin stabilized. So it only viewed the Earth roughly a quarter of the time while it was in orbit. But of course, we learned from these early missions, and the technology has greatly improved. And now we have this new generation of weather satellites defined by the Joint Polar Satellite System, which first launched back in 2011, so roughly 10 years ago, when SUMI NPP first launched. And now, thanks to VIIRS Imager, we have complete global coverage twice a day that offers a full color view of our planet. And as I mentioned, SUMI NPP launched the end of October in 2011. So we're a little over a month away from 10 years on orbit with VIIRS observations. And of course, we have a second VIIRS on NOAA 20, which is almost 4 years old. And we're all looking forward to a successful launch of JPSS 2, which is scheduled for roughly a year from now. And just from a polar orbiting satellite perspective, our operational programs, this is what we had before on the left with AVHRR. So we were limited to 6 bands and roughly 1 kilometer spatial resolution at nadir. And now with this new generation, we have VIIRS with 22 channels. We have the 16 moderate resolution bands, or M bands, at 750 meter resolution. The 5 high resolution imagery bands, or I bands, at 375 meter resolution. And of course, a very unique day-night band, which I will be talking more about. And of course, we have a lot of these same channels on our geostationary satellites now, GOES 16 and 17. But there are some things that VIIRS can do that none of the geostationary satellites can do, such as the high-resolution long-wave infrared band, I5, at 375 meter resolution. This is the highest resolution infrared information you can get on any operational satellite today. Now, that's not going to be the focus of my talk. I'm going to spend more time talking about other bands on VIIRS that you can't get on geostationary satellites, such as the day-night band, which is a low-light visible sensor capable of providing visible imagery at night. And I'll also be spending a lot of time talking about the channel M8, which is centered at 1.24 microns. And this is not on any existing or planned geostationary satellite. And this channel is very sensitive to the surface characteristics of snow and ice, as I will be talking about. Now, I do want to point out that the next generation European polar satellite program, METOP-SG, will have a very VIIRS-like imager called MET-Image that will have this 1.24 micron channel. And it will also have water vapor channels similar to MODIS, but it will not have any equivalent to the day-night band. And the first of these satellites is scheduled for launch in 2023, and NOAA will be acquiring and distributing the data much like they do with VIIRS and the other JPSS products. So VIIRS has a wide range of uses, as I'm sure many of you are familiar with, from aerosols and clouds to ocean surface properties, land surface properties, active fire detection and vegetation indices. And of course, there are also operational snow and ice products. But my role in the JPSS program has been part of the imagery team, where we evaluate all the imagery that VIIRS produces to make sure that it's high quality. We produce the near constant contrast product, which is a scaled form of the day-night band to make it easier to display day-night band imagery. And we also come up with the multispectral imagery products that we distribute to operational users like the National Weather Service. And so that it's this imagery focus that I will be talking to you about today. Now, I'm sure we're all familiar with the saying that a picture is worth 1,000 words. Much less well known is the classic line from the film Two for Tunisia, where he says, "Ah, my love, a million poets could try for 1,000,000 years and still describe but 3/8 of your beauty." Now, this quote is less well known because it's not actually from a classic film at all, but from a Simpsons send-up called Colorization Theater, making fun of the early attempts to colorize old black and white movies. And from an imagery perspective, this is actually apropos because oftentimes what we're doing is taking what used to only be visible in black and white and adding color to it, and hopefully adding value as well. Now, getting back to the original saying, though, that I would argue that a picture is actually worth more than 1,000 words. I mean, imagine seeing a picture versus being blindfolded and having someone next to you describing what's in the picture. And I also want to highlight the value of imagery with a couple of examples from the fire detection world, which is another area that I'm very active in. So I was recently told by an anonymous reviewer that you can't use the imagery itself to detect fires, that you need to do a quantitative fire detection retrieval. And, the essential component of a fire detection retrieval is you need to retrieve the latitudes and longitudes of all the pixels that contain fire. But imagine, for example, you are a fire manager, on the scene of a large wildfire, and you're very interested to see what has happened with the fire since the last satellite overpass. And I hand you a piece of paper, or in this digital age, a text file that just contains a list of latitudes and longitudes on it. Is that document going to be very useful for you? Or would it be better to see that same information presented in an image that's been geo-referenced to the Earth? So now you can see where that fire is. And by comparing it with previous images, you can see how that fire has evolved over time. And I've also heard through the years at various conferences, people kind of dismissively refer to satellite imagery as just being eye candy or pretty pictures, as though the images themselves don't have any value. But satellite imagery is actually a great way to communicate, what we do with the public. For example, here are a couple of examples of the National Weather Service sharing excellent day-night band images with the public, and it's easy for anyone to look at one of these images and digest the information in them. Now, satellite imagery really is a synergy between art and science. And as an example of that, here are 6 different ways of trying to discriminate snow and ice from clouds, for example. And, imagery is essentially a subjective thing, and it can come down to personal preferences. And it can also come down to our own sensitivity to color. Not everyone has the same sensitivity to color as everyone else. And what may look good to my eye, might not work for someone who has color vision deficiency, for example. And so we have to keep those kind of things in mind. And well, even though it's inherently subjective, there are a few guiding principles that we like to use in the imagery community. And the first is that you want to maximize the amount of information that you can present in the image. And I'll show a few more examples from the fire detection world. Starting with this case, this is an image that I lifted off of an old US Forest Service website many years ago. That website doesn't even exist anymore. But this was the early attempt by the Forest Service to use day-night band imagery to detect fires at night. And when I saw this image, my first thought was, where are the fires? Can you even tell where they are in this image? Does this image contain any useful information from a fire detection or management standpoint? And what I suspected they did is they just simply scaled the day-night band radiance values linearly between the maximum and minimum radiance observed in the scene to come up with this image. And so I took the same data and plotted it up in just that way, and you can see that there's very little information to be had. But watch what happens if you scale the image a lot more intelligently. Now you've brought out a lot more information, all the kinds of information that the day-night band can give you. So not only do you see the city lights, but you can also tell where the fires are. At least if you've looked at this imagery enough, that fires are these rings of light, oftentimes that look different from city lights, for example. And you can see evidence of some smoke in the atmosphere. You can see where the clouds are. You can see the fog filling in all these valleys along the coastal range. And this is all important information that a fire manager is going to want to know. How thick is that smoke? Is it going to impact our aircraft operations? Is that fog going to impact visibility? This is information that you just can't get from a poorly scaled image. And the other goal is to make it intuitive. You want it to be easy to understand, when you view the image. And so I'll compare and contrast 2 examples here from the National Weather Service using GO-16 to detect fires. And so the one on the left is just the 3.9 micron band displayed with the default color table that National Weather Service uses in their AWIPS display systems. And on the right is the fire temperature RGB, which is one of the products that I helped develop. And I would argue that one of these 2 is a lot more intuitive for users to grasp, especially if you're going to share these images on social media to try to inform the public. You know, I wonder how many members of the general public who aren't satellite meteorologists know that this black blob with the yellow dot in the center is the fire that they're supposed to be concerned with. Whereas the fire temperature RGB is designed to make fires look like fires. So it's a lot more intuitive. So I want to say a few words about the value of the day-night band. And for those of you who are unaware of the day-night band, it is perhaps the most powerful tool in the VIIRS arsenal. And basically, it's a set of detectors that are sensitive to radiation in the roughly the 500 to 900 nanometer range. So in the visible and near infrared portion of the spectrum. And it's very sensitive to low levels of light, you know, 8 orders of magnitude or so, less than full afternoon sunlight. So now you have visible imagery available to you at night, because you can see reflection off of clouds, for example, thanks to moonlight. You can see city lights in the imagery. You know, and that's another great thing, you know, certainly when it comes to monitoring hurricanes at night, you can get a sense of which communities might be affected. This was Hurricane Ida from a few weeks ago. And occasionally you'll see lightning flashes show up in the imagery. You'll see the aurora. And, you know, there are a lot of sources of light at night that we generally aren't aware of typically, but the day-night band can take advantage of all these different sources of light and provide valuable information. And so to highlight, you know, the value of having visible imagery at night, I'll compare and contrast the day-night band with what used to be the only way to know what was going on at night, and that is long-wave infrared imagery. And so I'll draw your attention to the image on the left, which is looking at the coast of Antarctica in the long-wave infrared. And it's very difficult to tell where Antarctica ends and the Southern Ocean begins. But if I show the day-night band image, that coastline becomes clear as day, you know, even though it might not be day at the time. If you look at the image on the right, this is an example over the Arctic, looking at the Chukchi Sea. And of course, you can see some of the features of the ice in this long-wave infrared image, because here there's a stronger temperature contrast between the ice and the open waters. But you'll also see this feature with a similar brightness temperature that you might correctly guess is a cloud. Now, if I display the day-night band image from the same time, you'll notice that you can see through that cloud to see these sea ice features more distinctly, because there are a lot of clouds in the atmosphere that are opaque in the long-wave infrared that the day-night band can actually see through because they're semi-transparent at visible wavelengths. And also, you know, getting back to the first case over Antarctica, those images came from around the time of a major calving incident on the Pine Island Glacier, and VIIRS captured that event quite well. It's also fun to remind people that yes, it does snow in Hawaii. And so here's an example looking at the big island of Hawaii, zoomed in on this inset. And you can see these bright areas on the top of Mauna Loa and Mauna Kea, which are actually regions of snow. And as I advance forward to the long-wave infrared image, it's very difficult to tell in the infrared that there is snow on the tops of those peaks. And also, as I toggle back and forth, I want to draw your attention to Haleakala, which is the highest peak on Maui. In the infrared, you can see that it's quite cool up on the top of that mountain, and you might suspect that it's cloudy, whereas the day-night band shows that it is cloud-free. And this was actually a high impact case because the National Weather Service had to issue winter storm warnings, and they had to close the road to the observatory because they got 4 to 6 inches of snow out of this event, and it created hazardous driving conditions on the road leading up to the observatory. And another example, just to drive this point home, here's a comparison between the day-night band on the left, where you can see this patch of ice floating around north of Alaska. And I defy anyone to tell me that they can actually see that ice in the long-wave infrared image on the right. Now, the day-night band is actually so powerful that you don't even need sunlight or moonlight to detect things. And not only can it detect city lights, it can actually detect the light emitted from ships. And so if you look at this example, you'll see this light traveling up a lead in the Arctic ice north of the Svalbard Islands. And this light will pause briefly before it splits into two. And one light will head back out toward the open waters, and the other light remains in the ice. And what you're actually seeing is the start of the Norwegian Young Sea Ice Cruise. This is a field experiment that took place back in the winter of 2015, where the icebreaker called the Svalbard was leading a research vessel called the Lance into the ice sheet. And the Lance was allowed to freeze with the ice and float around with it, so researchers could study how its properties evolved over the course of the winter. And this ability to detect ice, and the ship lights has been a big benefit for the National Weather Service, because the Alaska Sea Ice Program often has used the day-night band to rescue ships that got too close to the ice when they shouldn't have, and to help ships navigate their way through the ice as well. Now, this loop on the right is a 6-week animation showing how that ice moved around over the course of this intensive observation period from that field experiment. And what I want to point out is that both of these loops are from the winter in the Arctic, where there's no sunlight available. And for most of this time period, there's no moonlight available as well. And yet the day-night band is able to detect these ice features because it's sensitive enough to detect the light emissions from our own atmosphere that we know as air glow. And so you don't even need sunlight or moonlight available to you to be able to detect sea ice. Although you will notice in some of these images evidence of the aurora showing up as well. One of our active areas of research at CIRA is looking at optical flow techniques. And this is work that is credited to Jason Apke, who's an optical flow expert. And for those of you who are unfamiliar with optical flow, it is basically an objective analysis technique for determining motions between frames in an animation. And with so-called dense optical flow, you can actually retrieve a motion estimate at every single pixel, which is a lot better than the traditional cloud tracked or featured tracked methods for determining motions. And so one of our areas of research right now is looking at optical flow algorithms and seeing what they can reveal about the sea ice motion and comparing these with the more traditional ice motion techniques. Another recent project that I've been tangentially involved in is looking at the low clouds at night with the day-night band, because the day-night band can often see low clouds at night that maybe might be missed by the traditional infrared cloud detection techniques. And so we set out to prove that this was the case, and ended up finding in many situations that the reverse is true, that the VIIRS cloud mask is detecting clouds that the day-night band reveals aren't there. And the reason for this is because the VIIRS cloud mask uses this brightness temperature difference between the long wave infrared, the 10 micron channel, with the mid wave infrared to detect low clouds at night. And basically what that test is looking for is anywhere that brightness temperature difference is positive, because that's a sign that low clouds are present. So if you look at this image on the right, you can see a large area of positive brightness temperature differences. And sure enough, when you plot up the VIIRS cloud mask, it shows those regions as cloudy. But if you compare them with the day-night band image on the left, you see those areas are actually cloud-free. So the question is, what's going on here? Well, it turns out this brightness temperature difference works because there's an emissivity difference in low clouds between the long wave infrared and the 3.9 micron channel. And because of these emissivity differences, low clouds generally appear warmer in the long wave infrared than they do at 3.9. But the 3.9 micron channel is much less sensitive to the atmosphere. And so you can have a situation where the 3.9 is seeing all the way through the atmosphere to a cold surface underneath, yet the long wave infrared bands all have some sensitivity to lower atmospheric water vapor. So if you have a situation where you have a cold surface that is topped by a warm, moist boundary layer, you can get this brightness temperature difference that is a false alarm signal for low clouds. And so this really has an impact on any of the retrievals that use the VIIRS cloud mask to try to identify clear areas, because you might actually be masking clear areas that the VIIRS cloud mask thinks are cloudy. And so we're working with the VIIRS cloud mask team to help improve this cloud mask algorithm. I also want to mention that we have developed some multispectral imagery products that utilize the day-night band. And we are calling it the Snow Cloud Discriminator product for its ability to discriminate snow and ice from clouds. And I'll start off here with a true color image from VIIRS over our region here in Colorado. This is from a few years ago. And of course, with true color, it's very difficult to distinguish the snowy areas from the clouds because they both appear white in visible wavelengths. But we can bring in information from the other bands on VIIRS to now discriminate snow and ice from clouds, with the goal being to keep snow looking white, and then we highlight the clouds in various colors, with the low clouds in yellow and high clouds in magenta. And this product was first developed by Steve Miller, and he had been producing it many years during the daytime. But what do you do at night? Where there isn't always a strong temperature contrast between snowy areas and snow-free areas for the long wave infrared to key in on. But with the day-night band, you can see quite clearly where the snow is. You can see this nice swath of snow over the Palmer Divide south of Denver, for example. And much like during the daytime, we can use the day-night band at night combined with the information from the other infrared bands on VIIRS to do a similar snow cloud discriminator product at night. And I'll show another example here, looking at the day-night band image on its own over Alaska and the Yukon Territory of Canada. And we'll compare that with the snow cloud discriminator, which much more clearly shows where the clouds are in a region that might otherwise just appear white in the day-night band imagery by itself. And so this product uses the day-night band and 8 other VIIRS bands to highlight snow in white, and it colors the clouds. And so this is a good segue into talking about RGB composites, which is really my area of expertise. And the basic idea behind an RGB composite is it takes advantage of the way color is displayed on your computer monitor. Virtually every computer monitor has some form of the RGB color table on it. And so every color you see is expressed as an intensity value of red, green, and blue light emissions. And so what an RGB composite is it takes 3 different values. These can be the individual bands, they can be channel differences, or any other mathematical manipulation you want to on the data, just as long as you end up with 3 different values that you define as the red, green, or blue component. And in this way, you can combine 3 different images into one. And if you do it properly, you'll create a final image that has a lot more information in it than any of the individual components can provide. And so here's a classic example of an RGB composite where we set the high resolution visible band on VIIRS as the blue component. We take the 0.87 micron vegetation band as the green component, and the 1.6 micron snow and ice band as the red component. And then you get the RGB on the bottom. That looks very similar to a true color, except thanks to this 1.6 micron band, now you can start to discriminate ice clouds and snow and ice in these cyan colors compared to liquid clouds in white. And this RGB has gone by a number of different names over the years. I believe it was the group at EU MetSat who first popularized this RGB, and they call it natural color. So that's the term I most often use. But the National Weather Service ends up referring to it as the Dayland Cloud RGB. And one of the great things about this RGB is that you can produce it with the I bands on VIIRS, so at 375 meter resolution. And that really gives you a lot of detail, such as this ice flowing down the Alden and Lena rivers in central Siberia during the spring ice breakup season. You can see a lot of great detail in the ice motions over the Arctic, for example, as long as you have daylight available for these bands. And here's another example of this RGB looking over Antarctica. And all those wavy ripples that you see over the surface there are indications of blowing snow across the Antarctic plateau. Now, I do want to really highlight the 1.24 micron band on VIIRS, which, as I mentioned before, this is a channel that is not available on any existing geostationary satellite. And this channel is very highly sensitive to snow properties. And as you can see from this plot here, which is the reflectance spectra of snow as a function of grain size, you can see, what we all know, that snow is very highly reflective in the visible. And as you get into the infrared, you get to where snow and ice are very absorbing. And this 1.24 micron band is right in the transition zone between these two regimes. And you can see it's very highly sensitive to the reflectance, or it's highly sensitive to the grain size of snow, with snow being more reflective as the particle sizes are smaller, and less reflective as the particle sizes get larger. And we can use this information to detect things like snow and ice melt. And so here's an example looking at the ice sheet on top of Greenland from a couple of summers ago, where they had a major heat wave. You know, I know many of the towns on Greenland during this event made it into the mid 70s, which is almost unheard of for Greenland. And you can see over the course of the afternoon how the surface of this ice sheet darkens with time as melting is occurring. Take another example here over the Great Plains of the United States, starting with the visible channel on VIIRS and heading up in wavelength to the 0.86 micron, vegetation band, where again, in both of these bands, snow and ice are very highly reflective. Not much difference between the two. Then we get to M8, which is the 1.24 micron band. And now you can see the snow is starting to darken because it's less reflective than in the visible. And you can also see quite a gradient in the reflectance of the snow as it gets darker to the south. And you can also start to see this cloud show up over South Dakota that you couldn't see in the visible bands or the vegetation band. And then as you go further up the wavelength space, you get to the 1.6 micron band, where snow is almost uniformly absorbing and looks very dark, and the same holds true at 2.25 microns. From an RGB standpoint, we can compare the true color, which, as I mentioned, is tough to discriminate clouds from the snow. We have the natural color RGB, which I showed previously. Now you can see that cloud over South Dakota. And then we get a new product that I've been working on over the last couple of years that I call the Snowmelt RGB. And all we've done is replace the vegetation band from the natural color and replaced it with the 1.24 micron channel. And now snow is more blue than cyan in color, and it varies from light blue to dark blue depending on the snow grain size and depending on how much melting there is going on. I also want to point out that a group in France has developed their own snow RGB that utilizes this channel, and they scale everything to make snow orange, and well, it varies from orange to red. Now I'm going to zoom in here over this region of southern South Dakota to point out that both of these snow RGBs highlight this swath of fresh snow that is visible on top of the older snow that you can't see with either of the other two RGBs. So the Snowmelt RGB really is useful for identifying things like wet snow versus dry snow, or fresh versus old snow, because as snow ages, those finer particles are the first ones to sublimate or melt, leaving behind the larger particles. So snow will gradually darken over time in this RGB. But another thing we've found that it's useful for is identifying regions of mixed precipitation. So here's a case back around New Year's from last winter, where a storm hit between Kansas City and Omaha. And you can easily differentiate where the wintry mix occurred. That there was a region there that saw sleet and freezing rain, and of course, very wet snow where the temperatures were close to freezing, compared to where it was all snow further north and west in Nebraska, where temperatures were a lot colder. Here's another example looking at New England from a few winters ago. And you'll see this dark blue band show up from northern Rhode Island down into northern New Jersey. And this was a pretty significant ice storm that impacted the region. That shows up quite clearly in the Snowmelt RGB. And if you follow this S shape across Connecticut, you'll see that matches up quite well with a map of known power outages as a result of this event. Here's another case looking over the Dakotas and Minnesota, where you can see a swath of fresh snow be deposited that starts to melt over time. This is a 3-day loop, and you can see how that snow generally goes from the more cyan color early on to being more of a darker blue as the snow ages and melts. Here's another example from Alaska looking at swaths of fresh snow on top of old snow. And so you can see some streaky features, particularly when you zoom in, of swaths of fresh snow being deposited on top of the older snow. And you can also see rain on top of snow, or in this case, ice over the ice in Hudson Bay. And so you can see this swath that has the appearance of rain falling on top of the snow. Of course, there are very few observers out there to confirm that it did actually rain. There are no CIRA'S members out there, but it does have that ability in the Snowmelt RGB to identify rain on top of snow. Here's another interesting example looking at the ice over the Arctic from the summer of 2020, where this ice just north of Alaska here is very dark in color, and 5 days later goes from being very light in color. And in the intervening 5-day period, we assume that snow fell because it was very cloudy over that 5-day period. But it would be great to have some surface validation that this is in fact occurring. Here's an example looking over Antarctica with a melt event that occurred on the Ross ice shelf. So we have the band M8 on its own on the left, compared with the Snowmelt RGB on the right. And during this event, we had the downslope flow off of the Queen Maud Mountains, leading to warming and this swath of surface melting on the Ross ice shelf. But perhaps much more interesting was what happened just a few hundred kilometers to the left of this event. At the same time, I noticed there was this very bright feature in the ice over Antarctica that shows up in M8, and it shows up in the Snowmelt RGB, and it has very distinct edges, making me hard to believe that this is just a region of fresh snow on top of old snow. But I don't have any other better guesses as what could be going on. And of course, there are very few people on Antarctica to really observe this ice directly. And if the penguins know what's going on, they're not telling us either. So with the few minutes I have left, I'd like to take a moment and promote our SLIDER website, which is a great resource for viewing real-time satellite imagery. And so for those of you who are unaware of SLIDER, it's been around since the summer of 2017. And it was originally designed to display and loop imagery from the GOES-R satellites and Himawari, our new generation of geostationary satellites. And we display this imagery at real time and also at full zoom level. Now, shortly after this launch, we started asking ourselves, well, could we do something similar for VIIRS? And that's where Polar Slider came about. And so here's an example of what the Polar Slider looks like. And what we do is we stitch together images from each individual orbit into these hemispheric composites to always show the most recently available VIIRS data anywhere on Earth, in as close to real time as we can get it. And of course, you can loop the images as well. So here's an example of our Northern Hemisphere view, looking at our GeoColor product, which blends true color imagery during the day with a low cloud detection product at night. Here's the Southern Hemisphere view. Now we're looking at the day-night band for quite an impressive aurora event that took place over a 6-day period. And so you can really get a lot of spectacular detail looking at the aurora as well with the day-night band. And as I mentioned, all the imagery is available at full resolution. So for VIIRS, that means you can zoom all the way into 375 meters. And just this past spring, we added a couple of extra over zoom levels. So you can zoom in beyond full resolution to really dig into the see the full details of the image. And another feature we added this spring was a rotate feature. So you can always make sure that your region of interest is oriented right side up. And of course, right side up can be whatever direction you want it to be. Now, by default, we display imagery from both VIIRS instruments on SUMI MPP and NOAA 20. And since they're in the same orbital plane, but just separated by 50 minutes in time, roughly, it is almost like having your own geostationary satellite hovering over each pole. And is a great way to view the weather that's occurring on both poles. Now, we do get asked, what happens if I only want to see images from SUMI MPP or only NOAA 20? Well, in that case, you can adjust the time step setting. So instead of showing every image, which is 51 minutes apart, you adjust that to show every other image, and then you'll be looking at all the images from one or the other satellite. We have all 22 VIIRS bands available on a Polar Slider. And so I'll just run through a few examples. This was from shortly after the first sunrise on Antarctica back in September 2019. Again, with the high resolution visible band, you can see these blowing snow features along the mountains of the Trans-Antarctic range. And again, moving up in wavelength to the vegetation band and to the snow and ice band. Now you can more clearly see the clouds and differentiate them from the darker snow and ice. If you look at the long wave infrared, now you lose the information on that blowing snow, but you can actually get some sense of the winds. You can see the downslope warming. In this color table, actually the blues are warmer than the reds based on the way that color table was designed. Looking at the shortest wavelength on VIIRS, so band M1 at 0.41 microns, this channel is much more sensitive to the atmosphere than any of the other visible bands. So you lose a lot of the detail on that surface and just get a hazy appearance. And then we have the 1.38 micron CIRA'S band, which is actually a water vapor band in the near infrared, where water vapor basically absorbs everything except for whatever radiation is able to reflect off of clouds in the atmosphere. And of course, we have the day-night band on here as well, which works both day and night. And when you start to look at these images, you can often find interesting features. Here's another example of something that I observed in the imagery that I'm not exactly sure what's going on. But if you watch this loop, you'll see these interesting bright features show up over Antarctica. And the question is this evidence of blowing snow, or is, it's too small to be the aurora, surely, but it could be a polar stratospheric cloud, a cloud, way up in the stratosphere that really only the day-night band will see. This feature didn't show up in any of the other bands. We also have a wide variety of multispectral imagery products, ones that we develop here at CIRA, and also a lot of the RGB composites that are popular with users. So starting off with our GeoColor product, which I already mentioned, which is of course true color during the day. Then we have the natural color composite, which now highlights snow and ice in cyan colors. The day cloud phase distinction RGB is one of the more popular ones with the National Weather Service, and this highlights snow and ice in green. The day snow fog RGB highlights it in red. Then we have, of course, our Snowmelt RGB, showing ice in shades of blue, and the Meteo France version of the snow RGB, showing snow and ice in orange and red. And we do have our snow cloud discriminator product on here as well, although I forgot to include that in that example. We also have a lot of great features on SLIDER. So you can overlay products or channels, one on top of another, and vary the opacity to blend two products together. And one of the most popular products in this vein is the so-called sandwich product, which blends long-wave infrared imagery with visible imagery. And since we have the day-night band on VIIRS, we can now produce this sandwich product both day and night, since we now have visible imagery at night. You can also use the slider bar. So you'd slide that bar back and forth to more directly compare two products. We have a lot of other great features, such as a flow following feature, so you can move the imagery along with a particular storm. We have a mouse draw feature for easy annotations, and a share URL button, so you can easily share loops with your colleagues and friends. We have the full suite of JPSS cloud products on SLIDER as well. And we also have a new CAPS retrieval product, Cold Air Aloft, that we help develop here at CIRA. So the last option I'll mention is that you have the ability to download your own animated GIF, or we even have support for animated PNGs. Now, I do need to caution users that this is very memory intensive. And so if you try to download a very long loop, it might crash your browser, but you can always download the images separately and create your animation outside of SLIDER as well. So to summarize, hopefully I've instilled with you the idea that that pretty pictures do have value, even more than just being pretty pictures. And of course, the day-night band and the 1.24 micron bands provide valuable information that are not present on any existing geostationary satellite. And I also showed some highlights of the Snowmelt RGB and its applications. And if you want to view any of the products I talked about, you can always view them on Polar Slider by going to this link. Or if you have your smartphone on you, you can scan that QR code and it'll launch SLIDER. Although the default is to go to the geostationary version, so you'd have to choose JPSS from the satellite menu to be able to view Polar Slider. Thank you.